Okay. Hello everyone again. Today we want to study about artificial neural networks with Keras. Um, at first we study about biological neurons and then about logical computations with neurons and then perceptrons and multilayer perceptron and backpropagation training algorithms and also the regression MLPs and classification MLPs and how to install TensorFlow and how to build an image classifier using the sequential API. This is the image of a biological neuron. As you can see, it composes of a cell body, which includes nucleus and also some branches that are called dendrites, and also an extension which is called axon, and it is split to several branches that they called telodendria. And at the tip of the telodendria, there are synaptic terminals that they are in a close connection to other neurons. And also biological neurons produce a electrical signal, electrical impulse, which is called signal, that travels through the axon, and then this signal will activate the synaptic terminals that they can produce their own signals, which are called neurotransmitters. And if a neuron receives sufficient neurotransmitters in a few milliseconds, they can fire and they can produce their own signals to communicate with other neurons. We study the biological neuron because it is similar to the artificial neural network. So now we want to learn about
Nazanin, just go back to the other slide. This is a slide the medics on the call will appreciate and understand, correct? Sina, Elmira, even Bamisha, right? Because this is something we learn a lot in medical school, like these synapses, this is how joints move or anything else. So this is why there's a big, um, you know, thought that the neural networks work the same way like biological. Most of the examples use the brain, so you can imagine that we learn a lot of this, we see a lot of this imaging. Um, and that you always have these neurons, but this is a single unit. But when you put them in all together, and they're able to sense smell and or decide that I'm going to say something and then activate all those things that require the activation. This is something that for once, in addition to the confusion matrix, is very well understood by the medical people.
yes. And so each neuron can contact with lots of other neurons. And the artificial neural network is a machine learning model which is inspired by the network of biological neurons that found in our brains. And the first artificial neural network architecture presents a simplified computational model of a brain animal brains, uh, and it can compute simple computations using propositional logic. In the 1960s, most researchers before that thinks that they could soon be conversing with truly intelligent machines. But in the 1960s, this belief went unfulfilled. So ANNs entered a winter. And in the early 1980s, new architectures were invented and better training techniques were developed. So again, the artificial neural networks find its popularity. This is why current artificial neural networks will not lose their popularity. There are several reasons. For example, one of them is a huge quantity of data available to train each neural network, because as you know, neural networks, especially the deep ones, need lots of data to because they in this way they can be generalized well on the test set. And also the other reason is a tremendous increase in computing power. So each deep neural network and complex models can train in a reasonable time. And cloud platforms that have made this power accessible to everyone. The third reason is the training algorithms have been improved. Although they improved slightly, but these little improvements have a high impact on the performance of the algorithm. And some theoretical limitations of the ANNs have turned out to be benign in practice, such as the problem of local optima, because most of the people thought that the ANNs will get stuck in the local optima in practice. But in practice, this situation happen rare, and the ANNs can approach the global optima or near the global optima. And because of these reasons, ANNs seem to have entered a vicious circle of funding and progress.
So could you
And
um, so go back one more. Now, this is like the language or that you hear a lot when you hear about AI, and actually this was pretty common when we started to see a lot of AI applications in medicine. People would say the AI winter, you know, and so the AI winter here is that in these 1960s and 1980s, despite the promise of the artificial neural network, they were not making a significant gains. And when you look at something like support vector machines, then those became very, very strong and very good performance. So those took off. They didn't require too much computation. So when you hear AI winter, and people thought in the last few years that would have gone through another winter, I don't think that's going to happen. And go to your next slide. Is that the big thing here is huge quantity of data. Now, when we think about computer vision, the big data sets that have been there is ImageNet. ImageNet is a big data set that, has a lot of objects, labeled objects. And there have been some other like Coco data sets, and these ones have really emphasized and improved the uptake of, because you have not just large data sets, but large labeled data sets. So this is a big limitation when you think about medical imaging or medical machine learning. And in this case, what people want to do here is to say maybe we should have a call for a medical ImageNet. Now, Sina here has been doing annotations. That's not boring. Very, very takes a lot of time. And so, if you're starting to do that, to be able to curate a big data set requires quite a lot of effort, which is not cheap. And then now we know that the advent for cloud and computation was really around gaming. Because we got the graphical processing units. Remember, everything has to be made into zeros and ones. And as that got better, that's really driven the uptake. So a company like NVIDIA, which was just focused more on gaming, but most of those GPUs now are being used in machine learning. And if you look at Google, they've made their TPUs, tensor processing units, and so quite a bit of computation, and that's what powers Kaggle or Google Colab that allows us to get involved in machine learning with little effort. And so this, I just wanted to, because the wording here is going to provide this. I'm very excited that we're moving to this because this is what is thought of to be modern machine learning. I'm not saying that we should forget the other stuff before, but if you remember, I explained how, like the loss function works, right? And you have the gradient, function. And so you're at the top of the hill here. You need to come down to the hill, and you take many parts and you keep coming down, and you want to make sure that you come down here. And we're going to see what this means in terms of errors. Now, if you have sort of, because of different data, you may have several small peaks. So you may get here, but you know that this is the local maxima, local minimum, local optima, because the true global optima is here. And so this is what they thought, that the limitations of the future neural networks could maybe get tied here and would never come down to the minimum, and then you wouldn't be able to get a good circle. And so that stand out when you use a lot of parameters, that is not important. Okay, you can go on.
Okay. The artificial neural network, the artificial neuron actually can compute simple logical problems, and it has one or more binary inputs, which is on or off, and one binary output, and activates the outputs will activate when more than a certain number of inputs are activated. So here you can see 4 models, and we assume that the C, which is the output neuron, activates when receives 2 signals. The first one is the identity logic. So C is active when A is active, because it receives 2 signals from A. And here is the logical AND. C is active when both A and B are active. And here is logical OR. C is active when either A or B or both of them are active. And this one is more complex. And this C will active when A is on and B is off. And the first artificial neural network architecture was used to perform computations using propositional logics, like these logics we see here. The TLU, which is a threshold logic unit, is a kind of artificial neuron that can be used for simple linear binary classification, and it can compute a linear combination of inputs, we will see later. And if the result exceeds a threshold, it outputs the positive class. In the other case, it outputs the negative class. And training a TLU means finding the right weights values. Here is the architecture of a TLU. You can see 3 inputs here, and each input has a weight. And this is the output neuron. In this neuron, the weighted sum of the input will be computed, something like this. W1 x1 plus W2 x2, and then a step function will be applied on the Z, and this is the output. We will see the step
So,
function.
so the perceptron and the TLU is really the most basic um, component of the artificial neural network. You really have to focus on understanding this. And so you always have inputs, right? And once you always have inputs, um, all, everything, all inputs are seen by the TLU, right? So then every input will always have a weight, and you'll see later on the bias function. And in this TLU, it always has a step function that can be easily changed to, for example, a softmax. And if you remember, softmax just converts everything to a zero, 0 or 1 for your probability. And then, so this is a weighted sum of your weights and the inputs. And then it generates your output. And so this is like the basic, very, very basic structure of a neuron. And if you understand this, then it's going to be easy to understand like the multi-layer perceptron and all other things that are coming down in this chapter.
Yes. So now about the perceptron, which is one of the simplest artificial neural network architectures, and is simply composed of the single layer of a TLU. The inputs and outputs are numbers here, not a class probability like logistic regression or on or off values that we saw previously. And because of this reason, that the data, the output is not class probability, people always, most of the time, use logistic regression. And each input connection is associated with a weight, and the TLU computes a weighted sum of its inputs and then applies a step function to that sum. And also the common step functions that can be used in perceptron are Heaviside and sign function, activation functions. Here is the Heaviside, and this is the sign activation function. This is the architecture of a perceptron. As you can see, here we have two inputs, and each input will pass through a neuron that calls input neuron, and it has a bias neuron here, which always outputs 1. And we have an output layer here, which will compute the weighted sum of the input and then applies a step function or sign function on the output. And here is the output formula. And here X is the input, W is the weight, and B is the bias. And this one is the activation function, maybe a step function or a sign function here. And the learning rule for a perceptron is updating weights um, in order to reduce the loss. As you can see, Wij is the W of input I and output J, and will update the previous value of the W with the new one. And this is the learning rate, and this one Y is the output value, the target label of the output neuron, and this is the predicted value of the output neuron, which called Y hat, and X is again the input. But because the perceptrons were the simplest ANNs, So they had some limitations. They have now some limitations. Because of that, MLP, which is a multi-layer perceptron, can solve these limitations. One of these limitation is the perceptron cannot compute a model such as XOR, which is more complicated, but we can do that with a multi-layer perceptron. For example, here is a XOR function, XOR model, and if we have two 1 as input, we can go through the model and see what happens. For example, x2 is 1, so this is 1 and this is 1. The weights here are 1, and this one is 1 too. So we have 1 multiply with 1, which is the weight, and we have 2 and plus the 1 for this one, we have 2. And for the bias, we have minus 0.5. So we use this 2 minus 0.5. We have 1.5. And now when we apply a step function, the number greater than 1, greater than 0 is 1. So we have 1 here, and the weight is 1 again. So 1 multiplied with 1 is 1, and here we have 2 ones again, so 2, and minus 1.5, which is the bias term. So we have 0.5, and when we multiply it, we and 0.5 again after applying the step function is greater than 0, so we have 1. And when multiplied with minus 1, the weight here, we have 1 from this neuron and minus 1 from this neuron, and minus 0.5 the bias term. A number, and when we apply the step function, it becomes 0. So with two ones, we have 0 as an output. And here is the plot. So multi-layer perceptron has one input layer, which is path-through layer, and one or more layers of TLU, which we call hidden layers, and one final layer of TLU, which we call output layer. The layers that are close to the input layer are usually called lower layers, and the ones close to the outputs are usually called upper layers. Every layer except the output, such as here, every layer has a bias neuron, and is fully connected to the next layers. The fully connected layer means each neuron from that layer connected to all the neurons to the next layer. And multi-layer perceptrons can be used for regression and classification tasks. And this is the architecture of MLP. With 2 input neurons and 1 bias neuron, and 4 hidden neurons and 1 bias neuron again, and 3 output neurons, which you can see they are fully connected to all the neurons in the next layer. And from here, we can see that a deep neural network is a neural network that consists of too many hidden layers. For example, instead of one hidden layer, we have 300 hidden layers. And the next step is how to train MLP. We can use a backpropagation training algorithm, um, which consists of one forward and one backward pass, and computes the gradients of the network's error with regards to every single model parameters, the weights. And the steps are as follow. For each training instance, the model first get the input and pass through the input to the first hidden layer, and then it computes the output of that hidden layer and give the output to the next layer. And this will continue till the output neuron, um, in which the model makes predictions. This is the forward pass. And after that, the model predict a value. It measures the error based on the label value and the predicted value. And after that goes through each layer in reverse to measure the error contribution of each connection of the weights. And then it tweaks the connection weights to reduce the error using a gradient descent step. An important note here is to initialize all
Could
the
you go
hidden.
back?
Yes.
So we talked about this neuron, and imagine every neuron was a light bulb. Okay, so you obviously know Judy cannot draw, but so you have many light bulbs, and you had many streets. Okay, so all those are pathways and the layers, that the neuron will have to pass. So it's going to pass through many layers. So that's the forward pass. And the network is calculating. So you start with random weights, but you keep like calculating what your forward pass variables are. Then remember, everything that we have usually have an X and a Y and a Y label, but this is the training set. So for example, you may have a chest X-ray with a pneumonia label. And then you have your validation set. So you've not gone to your test completely because your test comes in when you've done everything, but your validation test will still have, X and a label, pneumonia or no pneumonia. So this is X train, Y train, and then X validation and Y validation. So you have at the end, so every pass, when you go through all the data up to the end, that run is called an epoch, So you'll see quite a lot of those words are used in neural networks. And when you get back to the end now, you have to say, well, I need to know, because the way the theory, this is the work of Geoff Hinton, who's the one who said radiology would be replaced. He's the one of the people who did this back propagation. And it's saying, I need to figure out which channels at every step contributed to the error and penalize them. So let's say the error is 2, and that means you're 2 points away from maybe a housing price or something like that. You are 2 digits off. So you penalize them, and it's almost like you're turning that light off. And then at the end, because you keep going back to every level and every layer, which is the back propagation, then you strengthen the signal of the people who are bringing you closer to the truth. And so that's the essence of now. You may never have to think about how that works, but that's a big component of how the modern neural networks work. They rely on this back propagation, and now people have tried to use this to do other interesting things that we won't talk about right now. For example, explainability. And also they're the ones that also contribute to the saliency maps. But yeah, okay. Uh, Everyone is very quiet, but I hope people are following. But we can continue.
Okay. An important note here is to initialize all the hidden layers connection weights randomly, because in other case the training will fail. Because if, for example, we initialize all the weights and biases to zero, all the neurons in the given layer will be perfectly identical. So the model will act as if it had only one neuron per layer, even if it has lots of neurons per layer. Instead, if we randomly initialize the weights, we break the symmetry. So allow the backpropagation to train a diverse team of neurons. And here we want to study about activation functions used in MLP. Uh, the a step function here will be replaced with other activation functions because the step function contains only flat segments. As you can see here, is the red one is the a step function, and here is the derivatives of the step function. And there is no gradient to work with. So instead of that, we use a sigmoid activation function. It has this formula and a tangent hyperbolic function, and also rectified linear unit function or ReLU. Here we can see the plots. This blue one is the tangent hyperbolic function. And as you can see, the output will be blue. So in this case, in comparison to the sigmoid, which is this one, the green one, the output will be around centered around the zero and can converge faster. And also the other activation function is ReLU, that it is zero for the non-values less than zero, and it is the Z for the values greater than zero. And as you can see, this ReLU activation is much faster than tangent hyperbolic and sigmoid. And this is the default activation function. Also, here is the derivatives of the function. This blue one is for tangent hyperbolic, and the green one is for sigmoid. And this is for the step function, which is always zero. And this purple one is for the ReLU. And why this is a question that we think about, because linearity, if we don't have activation functions, we just have a linear layers, can cause a stack of layers to be equivalent to a layer, so the model can't solve complex problems. And this is we saw that we can use MLPs for regression, and this is the regression MLP architecture. We have one input neuron per of many images with size of 28 to 28. We have 28 multiplied 28 input features. So we have this number of input neurons and barriers. It depends on the problem. We can use 1 to 5 hidden layers. It depends on the problem. But the output neuron is one per prediction. For example, I'll see it later. And about the hidden activation function, we can use ReLU. And about the output activation function, it depends on us. We can use none of the activation functions we talked about, but we can, in this case, we cannot guarantee that the output centered around a number or be positive. But if we want positive outputs, we can use a ReLU or a soft plus. Or if we want the output to be bounded around a specific number, we can use sigmoid or tangent hyperbolic. And the last function can be MSE or MAE, which we studied previously. And if we have lots of outliers, we can use Huber loss function.
Can I ask a question?
Yes, sure.
Okay, so again, I'm like at least 3 chapters behind, but I was wondering if you can explain why they're, when they're, like in the previous slide, when they were introducing the activation functions, they also introduced their derivatives. Do our like architecture use derivatives instead of the actual activation function to speed up the whole process, or what is the importance of that? Why they're like even talking about the derivatives here?
Yes, actually, each model use the derivatives of the inputs and to finally find the loss, and also in the forward pass and in the backward pass. Again, the model used the derivatives to find the amount of weight that can be updated, such as here. The model works with derivatives because it uses gradient descent.
And yeah, okay, so now I just got everything. Okay, thanks.
Okay, and here is a typical classification NLP architecture, because we also said that we can use MLP architecture for classification. For 3 kind of classification: a binary classification, or multi-label binary classification, or multi-class classification. A binary classification, for example, if we want to predict if a patient have a disease or not. So the input and hidden layers are same as the regression, but the output neurons would be 1. And we use the sigmoid activation function and binary cross entropy loss for binary classification. But for multi-label binary classification, for example, we have a image shows that if the patient has 3 kinds of diseases or not. Can you hear my voice?
I think it broke out for a bit. but we can hear you, or at least I couldn't hear you.
Yeah, you're back. You
For
just out for 1 second.
yes, for example, we have a chest X-ray image, and it shows if a patient has three kinds of diseases or not. This is a multi-label classification. For example, a patient may have two diseases at the same time. And the input and hidden layers are same as regression, but the output neuron would be one per label. For example, one for disease 1, one for disease 2, and other for disease 3. And the activation would be sigmoid, and the loss, again, cross entropy. But for multi-class classification, for example, we have an image, and we want to predict if it's a dog or cat or any kind of animal. So here we cannot have both dog and cat. So we have multiple classes, and the input and hidden layers for the model would be same as regression, and we have one output neuron per class. And the activation function that is used here is a softmax. As you know, it gives the probability of each class, and the sum of the probabilities would be 1 at the end. And we can use categorical cross entropy loss. Also, the model gives the probability of the positive class, and if we want to estimate the probability of the negative class, for example, binary classification, we can use the 1 minus the probability of the positive class. And here we want to study how we can implement these models, even using Keras or PyTorch to deep learning APIs. The Keras is a high-level deep learning API, and it's really easy to use, and allows to easily build and train or evaluate or execute all sorts of neural networks. And it relies on a computation backend. Because of that, we say multi-backend Keras. We can run Keras on TensorFlow or Microsoft Magnetic Toolkit or Theano or Apache MXNet or Apple's Core ML or JavaScript, TypeScript for running Keras on the web browser, and PlateML for using other GPUs than NVIDIA GPUs. But recently, TensorFlow itself, we can use the Keras of the TensorFlow, which will, for example, support TensorFlow's data API. And in this case, we can load or use data sets more efficiently. But PyTorch is somehow similar to Keras, is Facebook's library, but PyTorch is a lower level API which works with array expressions directly, and it's somehow hard to use in comparison to Keras. And its API to Keras, so you can switch between them if you learn one of them. And two limitations of PyTorch is the limited portability and there is no computation graph analysis, but it is much faster than Keras for using to train complex models. And this is the end of the slides for this side. If you have any question, we want to start the coding part. No one has question.
Let's start the coding part.
Okay. Okay. I want to we want to see the coding part from the book. After installing TensorFlow, you can use these commands even in Linux or on Windows for installing TensorFlow, and create a virtual environment and then install the TensorFlow. Before now, if you wanted to use the TensorFlow GPU, you have to install it separately. But now, if you install TensorFlow, you have both of the TensorFlow and TensorFlow GPU, I think. And these are the comments to see the versions of the TensorFlow. And for loading the data set, Keras provides some functions to load common data sets such as MNIST, CFAR, or fashion MNIST. And this is the way that we can import the data. We can, for example, here we want to use fashion MNIST, and we call the load data function. The data is split to two parts, one for training and one for testing. But if we want to have validations, such as somehow necessary in training a neural network, here we can split the data to train and validation. This is for the images, and this is for the labels. And here's the scikit-learn. Also we can load the data with scikit-learn, but there are two differences here. The Keras use the image array of 28 to 28 rather than 1D array. And also the pixel intensities are represented as integers here from 0 to 255 rather than floats. So here we should divide the input to have an input between 0 and 1, and divide it by 255.0 to convert it to float. So we can use it with gradient descent. And this is the classes we have in fashion MNIST, for example, t-shirt or top. And for example, we can get the first one, which is a code. And here's the data. Also, for creating a model, for building a model, we can use the sequential API. We can import it from keras.models.sequential. And before this, we have to import TensorFlow, Keras from TensorFlow. I think no, we will see it later. In this case, we have a simple model. For the first layer, we have a flattened layer, and we pass the input shape, which is 28 to 28 images. And we add a dense layer to the model, which has 300 neurons, and the activation function will be ReLU. This one has 100 neurons, the activation will be ReLU 2. And the last dense layer is for predicting the classes. Because of that, we always use the neurons same as the the number of classes. Here we have 10 classes, and we use the activation of softmax. So um, instead of the flattened layer, we can use keras.layers.input layer. They both do the same thing. Um, and also, if you want to know about the flattened layer, the flattened layer will reshape the input to a 1D array. So x dot reshape minus 1 and 1 will reshape the input to a 1D array. This is the other way of creating a model. We can use a list inside the sequential function. So here is the imports. We can use, for example, for adding a dense layer, we have to import it. We can use from keras.layers import dense. But if we want to use the keras of the TensorFlow, we can use from TensorFlow.keras.layers import dense. And also, this is other way of importing of this one. But people always, most of the time, use this one because it is short.
Yeah.
We can use model.summary to see some useful information about our model. We have the layers name, and also the output shape, and the number of parameters for each layer. For example, for the dense layer has lots of parameters. For example, for here, we have 300 weights multiplied to 784 for the input, plus 300 neuron, 300 for a bias, and the parameters will be too big. And at the end of the model.summary, we can see the total parameters of the model, and the trainable parameters and non-trainable parameters. Here we have just the trainable parameters, but for fine-tuning model, if we
Well,
see it later. Also, one useful, can you hear my voice?
yeah. Sorry.
Okay. Also, one useful function here is plotable. You can see the layers. Mm, mm. Okay, from here. Here is the code that we saw later. This is the use of a plot model. We can get this image. For example, the first layer is flattened input. The input is 28 to 28, and the output is 28 to 28, and shows the dense layers. We can easily access to the other layers with the name. We can, for example, use this model.layers. Model.layers will give the models layers, and we can access, for example, the first one, which is a dense layer, and we can get layer dense. We can get the layers with their names. Also, we have the get weights and set weights parameters. For example, for the first hidden layer, if we call the get weights, we get the arrays of weights and the arrays of biases. We can, should I continue or stop it here?
I guess we can stop. It's already 1 hour. The one thing I would say is that, so this chapter, is a good time to understand the terms used in machine learning. I know Elmira put in some references there in terms of like the tensor playboard and understanding what parameters you're tuning. So I'm going to encourage people for this one to try and actually run the code and experiment a lot. And that's because if we do that, we will be able to I think we're going to be able to do, this is like important. And once you understand what to do with things and what you're changing, I think it gets a little easier. So we'll finish this next time, but I would like to invoke Tim and Zach for the next one. Tim and Zach are participating in the Kaggle support devices challenge, is to maybe walk through their code next time to show us sort of like a simple way, maybe like 5 minutes, maybe Zach and Chima. You show us how you loaded the data, how you're tuning the hyperparameters, because what we should be talking about here is how do you, when I think about the code, I just need people to understand like this is like such a basic fundamental concept so that, and because I spend a lot of time with Tim and Zach, they know that, you'll be like, oh, well, did you randomly initialize your weight, right? How do you use a pre-trained network? How do you bring it in or something like that? Very important concepts to understand that's going to allow people to be able to play with actually some of the challenges. So the challenge right now that Zach and Chima are working on is one that takes, Chima has a very good slide on this, that takes 3 central lines, endotracheal tube and G-tube, and says, are they normal position, borderline, or abnormal? And so very good classification task. And so it would be great to even just run and hopefully we can give a total of 10 minutes to Zach and Chima on the next call for them to show us how they're loading their data and do something like that. Okay? Okay. Chima, what did you think about this chapter? What did you learn new?
So I think this chapter would have been reading this portion of the book, as I was reading it, I would have said like I would have needed this when I started, very very much when I started, because especially the Keras, especially Keras implementation and knowing how to use Keras. I was learning as I was going and I always looked it up. I looked up a lot of stuff. But I feel like the chapter really did a good job, especially towards the latter part of like explaining, oh, this is why this works. And this is why.
Yeah.
I think me and Zach, we picked up some stuff that we'll try, like
Okay.
in terms of how to represent our model.
Okay. And so I know that Chima has volunteered to be getting a summary of every chapter. So it's going to be interesting to see what you come up with this one. And we'll have you go through the summary, you know, maybe before then we jump to the next chapter or something like that.
Okay.
But that's going to be great. So naturally, I'll go to Zach. You two are brothers from a different mother, but brothers in crime. You're born together now.
Yeah, so similar to Chima, I thought this would have been really useful at the beginning because there were just so many functions that I felt like I either implemented from scratch or didn't really know about that would have just sped up the whole like beginning process of building the network and experimenting in the early phases. So I know in the future, instead of going through that long process, I can just do that more or less pretty quickly.
Okay. But Michelle, I know you're having internet connectivity problems. I think we lost Precious, but any thoughts? Have you caught up? You can type. Elmira, welcome back. What did you think of this chapter?
First of all, thank you, Nazanin, for putting all those together. I haven't had time to like go over anything. I just wanted to come here to like get some incentives, and I get that. Thank you. I have lots of questions to answer right now. The first one is to either refresh my memory on what the differences in 1D array data and like a 2D and multi-dimensional array data is. So, and why Keras is approaching these data as a 1D array as opposed to the, or maybe I'm just mixing them up, as opposed to the scikit-learn, which is treating it as a like 2D array or multi-dimensional array. And then I need to like understand that what makes one of them better than the other, or what are the uses of one or the other. And this is in addition to all the chapters that I've been missing. I'm gonna learn these.
Maybe you can tell us that the next time. I know the reason why I'm insisting on Zach and Tima to present a little bit of their code, or just walk through their code, is I think it's going to be an interesting process to see from end to end. But number two is that this week we were talking about data loading, correct?
Yep.
And if I look even ahead on the chapters of the book, there is one on data loading. So it's probably going to go to one of you for preparation if you want to just look at it. I think that's chapter loading and preprocessing data with TensorFlow 13, right? Chapter 13. And so, yeah, so, I mean, welcome back. We missed you, but we've been thinking about you, and we look forward to your energy and just questions and just perspectives on this. Me and you will catch up on separate time once you've shaken off the core exam preparation feeling. Okay. Sina, where are you today? I noticed you didn't give me a compliment on my Hawaiian.
Oh yeah, I was gonna tell you, you got it working. I wasn't sure if it was just today or how you've been sitting up in Hawaii or whatever that is. So yeah, kudos to you. I know it was good. It was good today. It feels like going from learning about Krebs cycle and amino acids to reading images of the liver. So it's more applicable.
Yes.
And I feel like this is what you read when you read about these big projects they're working on. So it's nice to be here, and it really I really appreciated going through the basics and overview and then doing the heavy math. So your brain is kind of primed. So I think it was well done.
Awesome. Toby, where's that picture? Did you change the picture? Let's see. Move. Oh, it's the same picture. Have you learned nothing all week, man?
Well, I have, but I've not had time to even use the marker board.
Oh no, the beards are growing too. You know, in America, you have to shave yourself. It's not like Africa.
Yeah, so that's why I have my clipper, but I'm still a bit scared. I don't want to spoil my hair.
Okay. Elmira is close by now.
I'm still keeping it.
I like that whiteboard you have.
Yeah, but it's not changed. It's still the picture of the eye.
You're not changing your ideas.
Okay, Toby, what did you think? Did you have a chance to go through it? I know you were super.
No, I did not have a chance to go through the chapter, but from Nazanine's explanation, I learned a lot. And one of the things I actually learned that I liked was when she compared Keras and PyTorch, because I never knew that Keras is high level and PyTorch is low level. I thought probably they were both low levels initially. So seeing that comparison helped.
Awesome.
Created some knowledge gap. Thank you, Nazani.
Awesome.
You're welcome.
Thank you, Nazarene.
Okay, so I think I've called on everyone, right? I shamed everyone. Okay. So Nazanin, what did you learn from preparing this chapter?
Actually, I was somehow familiar with this chapter because especially the coding part, because I do the same things for my projects, but about the biological neurons or the first neurons, I learned about them because I didn't know the exact history of that.
Awesome. Okay, I really enjoyed this chapter. I know no one has asked me what I learned, but I really enjoyed this chapter a lot, actually. And I hope next week, as we wrap up this chapter and see some real life code, actually using radiology images, see some results, it's going to really inspire a couple of people to just run notebooks and just see what they can do. You know, I saw in the process when I was doing this, and you know, and we're going to get close to the end of here, and then we're going to move to Jeremy Howard's book, which is very practical. You're always just building stuff and building things. So that's going to be interesting. But what I want you to know and go back here is when I say this is my epoch, and I know someone like Sena, I've been sending him to review more papers now. You know, I want this vocabulary for you to be very, very, like, you know, on top of your mind. You know that, oh, this is a classification task. I know that I should be using a confusion matrix, and these are the metrics that I should be using for evaluation. But if it's a housing prediction task, you know, it's a regression task, you know, then it's the MAE or an MSC, and now we learned a new scoring. Or this is my loss function, and when should you use, you know, I think that's the next thing, but when should you use what type of loss function, because you're thinking about your data. I think the next section talks even about data imbalance, right? So when you don't have enough data, what do you do with those things? And if for you to understand those things, even if honestly, this is the point where, you know, Zach, you know, Chima, Toby can build the model for you, but if you can actually take it over from there, and now this is like building a model from scratch. But the next one that we know quite a lot that we do of is pre-training. So this model uses, the weights are not random, they're initialized maybe using what we call the ImageNet weights or something like that. And what does that mean? So those are the rich discussions that I expect that we will be having. So I just need for you to reflect on this chapter a lot, because it's going to be the basic fundamental of understanding more deep learning and deciding, oh, okay, I know why this is not performing well. In the near future, one of the things that I do want us to review, and on the next one, and I'm just trying to give you also tips, Nazanin, for things that we want to hear, is when you look at the 30 epochs, you know, the 30 runs, and you can see that these 30 runs are going through all the data, is, you know, how do you start to see how are you overfitting? How do you interpret, you know, validation curves? How do you interpret error curves? So think more practical and think about what would you want to explain to people who do not know or do not build these models a lot. And those questions are very common, right? When we look at the confusion matrix and we're like, oh, that curve doesn't look okay. And if it on the TensorFlow board, playground, if you looked at some videos, they can show you things that will be like, oh, this error loss is too high or something like that. Because once you start to understand those things, guys, the rest is changing a model. And the bigger thing is understanding how your model is performing and why it's failing. And that's going to be a very good place to get to. Okay.
Yes.
Okay, fine. Well, I'll let everyone enjoy their cold Saturday. It's pretty dull here in Atlanta, but I look forward to catching up and finishing up on this chapter next week, okay?
Sure.
Awesome.
Thank you.
Okay,
Thank you.
bye.
Thank
Thank
you.
you.